Good. So we've stared at this guy a little bit, and I alluded to this super quickly the other day, but I just want you to notice there's another concept here. So in the same exact column from modulus of elasticity, which you now have a sense of because it's the relationship between stress and strain. But notice right next to it, there's also something called a modulus of, but it says the modulus of rigidity. So modulus of elasticity is E, but modulus of rigidity. And notice they kind of almost sound like the same thing, don't you? It's like rigid, elastic. I mean, like elastic is, I'm thinking elastic is just the flexible word for it. And rigid is like, well, not flexible. I stare at that and think, well, why is that in there? Like, what is that? Like, is it the same exact thing? I don't really get it. What's going down with that? Well, let's stare at that a little bit in context of this problem. And so this is really I'll just kind of introduce it here because this problem won't take that much space, but 3.6 is titled shear stress strain diagrams. Not stress strain diagram or normal stress strain diagram, which is what we looked at before, but shear stress strain. So again, we've highlighted this, but I got some object that looks like this. This is in the normal direction, whereas that is in the shear direction. And so, cool. Well, you may remember shear strain was actually the angle thing. Remember how we kind of barely looked at that? We said, what does it mean when something strains in shear? And we said, that's kind of the strain based on an angle. And so, you know, if I push on something from the side, like this lunge container right here that used to be whole, it's gonna bend unless I push it too far.
Is that modulus of rigidity high?
Yeah, it's got a high rigidity.
So higher rigidity is like brittleness almost, like
Yeah.
brittle something else.
So, I mean, the point is when when you push on it this way, it's not going to do that. When I push on it sideways, it's going to change shape. Does that make sense? And so that's what shear strain meant. We measured it with an angle. And shear stress, remember, was just the same thing as before. In other words, you got that cross-sectional area. It's just a different force. It's that force. Let's see, what was the letter for that? I'm just going to write this in here, even though you don't necessarily need to know this, but shear, let's see, all of a sudden I'm actually blanking. What was the letter for that? Shear strain. I guess I'll have to look. I think that was in this section. Shear strain, did we have that here yet?
Are you saying like tau?
I think it is tau. Was that in the first section?
It wasn't in our notes. I ran into this on our 3.7 homework, so I thought there was 2 on Tuesday. And I had to do a lot of Googling on what modulus of rigidity was.
Got it.
But it
Yeah.
was like tau over gamma.
Yeah, so that's actually what's coming up right now. But yeah, I mean, so it was, we did do this. There's shear strain and shear stress, just like there's normal strain and normal stress. So let's stare at this for just a second. So this was actually the previous section. So what we studied, if you will, recently is that normal stress sigma and normal strain epsilon were related to each other, right? And there was a multiplier between them, and we called that modulus of elasticity. Well, the same thing is true for those yellow ones. There's shear stress, which is also just a force divided by an area. It's just that force is sideways. It's perpendicular kind of to the shape. And so that's what shear stress was. And it's just because that's in the shear direction. And there's also shear strain, which I just mentioned a minute ago. And notice that's an angle down here. And so it turns out, well, those are related too. And they're related in exactly the same way. There's a diagram for that. And you're given one in this exact problem right here. So notice, you don't notice it at a glance. And as a matter of fact, when I was kind of keying this, I didn't even notice it. I was thinking, oh, that's a shear strain diagram. Well, no, it isn't, because notice that's called tau up there. So that's actually shear stress. And this gamma, that's the first time we've written, no, it's not the first time we ran into that, but that's another wonderful Greek letter. This is shear strain. So notice the only thing that tells you that, and this is those tiny little Greek letters. In the previous one, this was sigma up here, and this was epsilon down there. And so it's understandable why somebody would stare at that and kind of just not notice that this is a totally different diagram. But interestingly, notice it kind of has the same characteristics. This isn't a complete shear strain, shear stress strain diagram, but notice it has that same kind of slope relationship in it. And what we're going to look at today is basically that rise over that run, if that's tau, and this is gamma. That if you take the rise divided by the run for the slope, that's just got a different number. So it kind of makes sense because it is the same thing. It's actually the same thing. It's just we're talking about a shear force, not a normal force. So it is the same number. That's why, and notice they just kind of picked a different word. They could have called it, you know, one was modulus of elasticity. They could have said normal modulus of elasticity and then normal or shear modulus of elasticity. They are both they are both pertaining to elasticity. And so I think they chose elasticity and rigidity just because they're kind of synonyms of each other. Again, I'm just trying to make some sense of this stuff. And so anyway, let's see if we can get this problem right. So the lap joint is connected together using a 1.25 inch diameter bolt. So I'm thinking to myself, bolt, bolt, bolt. Oh yeah, there we go. There's the bolt that has a 1.25 inch diameter. That's huge, by the way, 1 inch diameter bolt. That's massive. So, okay, got that. The bolt's made from a material having a shear stress strain diagram that is approximated as shown. Notice, and I'll just do this now since of what I showed you just a second ago, notice they kind of gave us a reading for it. In other words, in our problem here, if G is tau, which notice is 50, and notice it's KSI, so I'm actually going to write PSI because I always get bothered by that. So it's 50,000 PSI divided by gamma. Notice that's 0.005. Notice what the unit of that is. What's the unit of 0.005? Radians. Remember, that's a unitless measurement. It's kind of like you say radians, but it doesn't mean anything. Could you explain that to somebody? I'll just quickly go over something in math here really quick. My guess is not. But it's like if I want to describe something moving in this way as opposed to forwards and backwards and all that kind of stuff, you know, we think, oh yeah, degrees, I can talk about that. And that's great. And that's a unit you're stuck with. We're going to see this come up a bunch in the next couple of weeks. But the fact that we have a way to talk about an angle that has no unit is utterly essential. So what did we do? We said, well, okay, cool. I know that I can turn, you know, up to there, and I might call that 70 degrees. Cool. But what we did instead in math classes is we said, let's call that distance a distance of 1, not 1 inch, just 1, unitless length of 1. So does it make sense the circumference of this circle is 2 times pi times radius of 1, not 1 centimeter, not 1 inch, but just 1. Therefore, the distance around this circle is 2 pi, or about 6.28. And so does it make sense if the distance around this circle is 6.28 as a unit circle, as a unitless circle, then I can also get to this spot by just saying some proportion of that, full lap all the way around is 6.28. So that's what this is saying. It's saying we just broke our container a certain number of, well, not degrees, but radians. But when you say radians, it's like not really there. You see what I'm saying? So
That was a very circle.
it's not too bad, is it? It's a miracle. So I guess the reason I point that out is this is not a percentage this time. Does that make sense? Epsilon was a percentage that something got longer or shorter. This is not a percentage of the way something's angle changed because an angle's got it, well, be an angle. It's not a distance. So that's not a percentage. It's an angle measurement. So interestingly, I can actually divide that and get an answer. Flip. I already did this, so let's not do it again. So if you do that, you get I'm looking at this now thinking, wait, something's not right here. Oh, that's right. Yeah. Anyway, I just never wrote it down. And maybe you can predict, as I'm just suddenly thinking, that when I divide 50,000 by that tiny of a number, it's just going to go off the charts. It's going to be a gigantic number. So I have so many zeros, I can't even count them. It's like, I think 7 zeros. So, you know, that would turn into mega pounds per square inch or something crazy like that, whatever. Okay, great. Anyway, we can actually see what that number is. Okay, so fine. As you can appreciate though, you know, where are you going to get G most of the time? Are you going to look it up on some graph like that? No, you're just going to flip open to that table I just gave you. And as soon as you know what material it is, it's like, oh yeah, there's the G value. Great. So determine the shear strain developed in the shear plane of the bolt. Is that a confusing statement to you? I think it is to me a little bit. Determine the shear strain developed in the shear plane of the bolt with 75 kips on it. Yeah, totally mathematical, Dr. Seuss. Well said. But again, can you picture in that situation that this is the scissors chopping the bolt in half? This is two things sliding past, as I showed you. It's like this going in this direction and just chopping it off, chopping the neck off of that thing. But do you notice that if that brown piece of wood were to pull out, that it actually has to chop the bolt two different places? So that's exactly why there's kind of a P/2 over there. So anyway, you can sort of quickly see that. But because of that, you know, P over here being divided by 2, does it make sense that shear? And again, do you see that as a shear force? In a sense, this would be better if they called this kind of like V, because isn't that perpendicular to the bolt? So it's not wrong to call it pounds, that's fine, but because of the direction it's in, it's not pulling the bolt normally, making it longer, like we just studied. We're about now sort of pulling it sideways, ripping it, and so this is kind of V. So in the end, I'd be dividing by 2, so I can sort of say that shear force would be, well, whatever half of that is, which is 37.5 kips. So I think I'll just leave that in there as V/2, just so you're thinking about the difference between shear and normal stresses. Okay, cool. And then, as I just looked up with you a second ago, the shear strain, tau, is V over the area. So shear strain, or is it shear stress? Actually, I'm thinking out loud when I say that. I think this is actually shear stress. Yeah. Language of this is hard, right? So yeah, that's right. You know, again, I'm the teacher and this isn't sticking in my head very well. Shear strain, that's right. That was the angle. Shear stress. So that makes sense because stress is a force divided by an area. That's what stress is. So, okay, great. The only shear part of it is just saying what direction that force is coming from. So I'm going to write up here shear stress since I screwed it up. Okay, so cool. I know the V, 37.5 kips. I know the area. Well, I don't, but I can take the area formula. I would have just cut 1.25 diameter in half, except for it's such a weird number. If they'd have said it was something like 1.4 inches in diameter, I would have said, oh, 0.7 is the radius, and I would have said pi r squared. But in this case, it's hard to cut in half, so I'm going to say pi over 4 times that. And I'm paying attention to inches here just to make sure I don't screw this up. So it's that many inches, but then that quantity is squared. So, okay, that's just a number. I can calc that. You get either 30.6 kips, well, kips per square inch. And again, I find these units really hard because when I see kips, I want to say that that is already like per square inch, but no, it's just 37,000 pounds divided by square inches. Oh yeah, that'd be PSI. So you get 30,000 PSI or 30.6, as your book would say it, KSI. KIPS and KSI are different. That just bugs me. So great, I know shear stress, KSI. Now what they're asking though is determine what the shear strain would be. We just found the shear stress, but what's the shear strain? And again, I'm thinking out loud, kind of making sure I understand this, reminding you shear stress is like PSI, whereas shear strain is like an angle. So how am I supposed to get from one to the other? Well, see, that's what we've been studying. That's the chart. That's the G. The G is the slope there. So if I go back over to this graph and I say, hey, I just got a value of 30.6 KSI. Well, notice the units over there. 50 was KSI, so wouldn't 30.6 be like right there? And so the chart or the G is going to allow me to make that conversion. So if I say, okay, cool, look, I got over there. And so I can see it's going to be less than 0.005. Well, that's what this relationship is really getting at. So let's see, is that in this note sheet or the previous one? In a sense, this is the relationship that I've got here. As I said before, usually you're just going to look up G in the back of the book as opposed to stealing it off of a graph like this. But if I know both this tau value and that G value, then I should be able to solve for that, because you can appreciate that's not an easy calculation to make. And we only did a problem or two like that. But remember when you squish something and you're measuring the angles, it was all kind of weird. This is kind of a neat relationship, because if you can find the shear stress, then you can just use G to get the shear strain, the angle change, if you will. Oh, okay, cool. So since G is equal to tau divided by shear by sigma. And I think in the interest of kind of, rather than divide 50,000 by, well, maybe I'll write it up here. I think that was a 1 with 7 zeros, as I said before. If I would see my calculator right. So 10,000 PSI. So then I could say, cool, 10,000 PSI is equal to our 30.6, well, not 30.6, but 30,600. Notice the units there. What are the units on the bottom then? This is interesting. This is what I was talking about earlier. Notice it's already PSI equals PSI, so there better be no units down there. So what does this angle have to be in? It's got to be in radians. Isn't that kind of weird, kind of cool? It's almost like the way I like to explain it when I teach it is radians are actually the way you measure angles in the universe, if you will. We sort of superimpose the 360-day Gregorian calendar year. And so we said, okay, the Earth moves, we made it Earth-centric. Like the Earth moves 1 degree a day. So that kind of makes sense why we would do that, but it doesn't work here. If you put degrees in there, then the units are all screwed up because degrees are actually a thing. So anywho, if I rounded that number off, it's actually a little bit better than that. But if you solve that for sigma, then you get approximately 0.00306. Now, if you look in the back of the book, that might not be the answer you find back there, because remember there's degrees and radians, and it seems like your author switches it to degrees a lot, which I actually kind of agree with, because that's how we think. But how do you convert? You should be able to reason this out. If I say 0.00306 radians, and I want to end up in degrees, you should be able to let units tell you what to do here. This should not be one of those things you have to memorize. Should make sense to you that if I want radians gone, then I'm going to have a version of it on the bottom so that they can cancel, and then degrees on the top. And so, oh, look, that would turn into degrees. And then you just have to go figure out what the conversion is. Oh, we just figured out a second ago, in 360 degrees, there's 2 pi radians. Or you could say in 180 degrees, there's 1 radian. And so what you're really doing is taking that number times 180 divided by pi, which I find personally, I will have memorized if I'm using it a bunch, which I've found myself doing in this chapter and later chapters in this class. But as soon as I'm gone for more than a month, then it's gone. And then I have to use logic to make it for myself, which is kind of cool. Build your own tool. So I will say times 180 divided by pi, 0.17, 0.18. But of course, if you're saying degrees, you got to actually have the unit there. You can kind of be lazy and leave it off for the other one because there really isn't a unit there. Now, I don't think I assigned anything that you need this for, but look at this. This is kind of cool. This is just on your note sheet. So I'm just kind of highlighting modulus of elasticity or modulus of elasticity. So there's kind of 2 names for this that are in your book. Shear modulus of elasticity. So the original one was just modulus of elasticity, whereas this is shear modulus of elasticity. I kind of like that better because it's like then they're both elasticity. Or you can just say modulus of elastic rigidity and then get rid of the shear part of it. Either way, whatever, G. And so it's proportionate just like E was. So that's kind of cool. But then notice this. This is kind of an interesting formula. Stare at that for a second. Like, what is that actually saying? Ultimately, it's just saying that G and E are related to each other. What's that V stand for again? It's not really V, it was nu. What was that in the last section? That was Poisson's ratio. So oddly, what this formula is really saying is you could, I mean, aren't all 3 of those terms something you could look up in the back of the table? So interestingly, you can convert, you can work your way around. Like if you knew G and E, then you could figure out Poisson's ratio. The part of that would be interesting, I think, would be the fact that you could probably measure G and E, like pulling on something and make that little graph, and then, you know, use this formula to divide them and come up with Poisson's ratio. That's kind of interesting. Maybe that'd be an easier way to measure it, if you will. Like I said, I don't think you need this in your assignment for anything, just based on what I happen to assign. But that's just kind of cool to notice that, you know, all of these things are connected, related. Fascinating.
So on the test, if we get a question like this, do you want us to convert it to degrees or equal?
I don't care. Yeah, care less. Stop with radians. My attitude is always like stop on it as soon as you possibly can.
Correct.
I'll calculate them both just if I'm grading yours to make sure that. Okay. So now we are going to see how far we can get into. We're only going to cover one section. Unfortunately, it's not bad, which is 4.2. So we're actually done with chapter 3. Now we're looking at chapter 4. Let's see, how do I want to get into this? Actually, I think I'll point this out since I'm sitting here. This is the only equation that we need for this section. Yay, more Greek letters. What a shock. Fortunately, you know most of the letters in this formula. And then I want to show you some cool things about this formula in a second. Right now, I'm just pointing it out. But elastic means something is flexible, right? What does deformation mean? Not defecation. I mean, get your mind out of the gutter.
You said I have lipstick.
What does deformation mean? What does something mean if it's deformed?
It's probably gone past the elastic region.
Doesn't have to,
No.
but the point is it's
Stretch.
stretching. Yeah, it's changing shape. And you're right, it can go so far, but it doesn't imply that it either has or has not. It's just deforming. It's changing shape. And in one sense, didn't we already study this? Like, isn't that what? Let's see. Isn't that just sitting on here somewhere? Actually, I think that was even in the previous section. No, this. Like this strain business right here. Like we saw something change length, like this formula right here.
Change it now.
And so what we did last time is we said, usually when you pull on something axially, you're thinking about how much longer did it get. But we even saw, thanks to Poisson's ratio, that the sides are going to get smaller when this gets longer. And so there's a way to figure even that out. So when something deforms, it's just changing shape. And we already did that, like strain, that E epsilon number for strain was a percentage. And it's the percentage of the change of L divided by the original L. And it's like, and so what is this section saying? It's saying, let's find elastic deformation. We already did this. What is it even doing in this section? Well, I want to show you something kind of cool. So here's this formula saying elastic deformation. Well, here's how you get it. Notice that's delta there, which is a change, like that's calculus, the change of something. So they're using delta. I think that's the lowercase, the one that we often use, I think is the uppercase one, which is that symbol for delta. So it just means change of something. The only difference is in the other one, epsilon was a percentage, whereas this is actually an amount. Like this is literally inches or something like that, which is what we did before anyway. And then on the other side, there's things we recognize, like N is the normal force, L is the length, A is the area of the cross section, and E is that modulus of elasticity. So it's like these are all things that we've messed with before. But I want to show you something here. Watch this. This is kind of interesting because when I first looked at this is an example of like what makes classes like this so confusing if nobody explains this. And I didn't see your author even explained it. And frankly, it was just a good luck on my part that it occurred to me like we already did this. Like what is this? I don't get it. Well, watch if I mess around with this equation a little bit. So I'm just going to write here, literally this, just so that you understand it, like this is inches or something like that. That's what delta is inches. Well, watch what happens if I do a little algebra here. If I take that delta and I divide L over to the other side, isn't that what we just saw a second ago? Like epsilon is equal to the change of L over the top of L. Like, isn't that what that is? Like, aren't those identical? They are. Delta is how much something changed, and it was divided by the original L. Well, what's left on the other side? Left on the other side is N over A, and then there's an E down there on the bottom too. Does that make sense? Well, where have we seen N over A before?
Oh, it's the normal force over the area, sigma.
That's sigma.
Normal stress.
That's normal stress. N over A was normal stress. And so if this side is actually just epsilon, and this side is sigma, and then there's an E down on the bottom, this is like the same formula we already used. Like they just made it from previous stuff. The only advantage of it, I guess, is that on this side is, not a percent, but it's just a length. So there's part of me that's like, what does this even do in here? Like I already know this, if you will. So isn't it kind of cool? Like it, in one sense, it's like, yeah, pile it on, man. Where's my next formula? Where's my next Greek letter? I'm dying in here, and you're watching me like can't even keep straight the letters. And it's the same for me as it is for you. I'm trying to keep all that stuff straight. But it's like the cool thing is conceptually, there's a lot of this stuff that belongs together, right? It isn't just some brand new equation from nowhere. So it's just kind of interesting to know. You don't need to know that for any reason. It's just kind of cool.
So wouldn't it be easier to have normal stress instead of the N over A?
Yeah. So, I mean, does it make sense? They could have given us this formula as delta equals sigma L over E or something like that. Yep, that could be the formula. The only advantage of it is that, in the problems in this section, you'll find yourself going, oh yeah, that's a neat way to write this formula, because when you look at a problem, don't you a lot of times know the forces on it? Like if you look at it, there's a force on it, right? And then it's like, oh, it's a certain shape. And so it's got an area, and oh, look how long it is. Does it make sense? Area is the cross-sectional dimensions and length is the length dimensions. It's like, so L and A are just the size of the thing, and N is the force on it. And then E is like, what material is it? So it's actually kind of a cool way to write it if you think about it. Is it kind of neat? So armed with that little intro, let's dive into this. And again, I think you'll sort of feel that this is neat knowledge. Like this is something I would definitely want to know. And so notice what they're asking me here before we kind of read the details of this. says determine the displacement of B with respect to C. In other words, hey, here's this object, this bunch of pipes or something on it. It's got these forces pushing and pulling on it. And notice they're really different. Aluminum, copper, steel, like there's all different materials. And after you pull and push on it, of course, it's going to deform. It's elastic material, and so it's going to deform. It's going to get longer. It's going to get shorter. And it's going to do that based on how sturdy it is. Its E value. Is it rigid? Is it really rigid? Well, then it's not going to get much longer or shorter. If it's not very rigid, then it's going to get a lot longer and a lot shorter. So the idea is, I got some metal in this car and I'm going to put a bunch of forces on it. You do need to know ahead of time, like, how's it going to change? This is not a big, this is belongs with what we discussed on Tuesday in the sense that we pulled on the block of steel and we saw it change sizes. That's all this is saying. It's no different. It's just that now, if you will, the fundamental formula is delta. Actually, let me check really quick in my note sheet. Did I say that someplace on here? Notice down here, I told you N is the normal axial force, L is the length, A is the cross-sectional area, E is the modulus. I should have also said that sigma is the length change so that you knew it's a length, not a percentage. Says that, I was just thinking that belongs on the sheet somewhere, so you know what that number is, or what that letter actually stands for. So that's probably something I'll fix, because it seems like that's important. So anyway, make a note of that for now for yourself. So we said that is equal to N times L over A times E. So great, it's like I could figure all that stuff out. But notice I've got sort of 3 different sections on this particular shape. And so that feels a lot worse than just one. And I guess you could say that's the jump here. We did this for one single bar the other day, but now we got this kind of item that's made of 3 different ones. And so could I still kind of pull this off? Now, so let's just play with this and see if we can get it right. Let's see, is there anything else I need to see there? No. So just to highlight this, notice it's got like A, B, B, C, C, D. So I'm going to say A to B. I got to look at that. I've also got to get down here and look at from B to C. Again, because they're all different materials, I've got to think about this. Now, here's the tricky part that gets, it's not tricky, but it's like something you have to still know from last term. And that is this, like, what's going on over here at AB? Like, what forces are on it? Well, I certainly see 2,000 pounds, 2 kips, 2,000 pounds pulling left, but notice there's a bunch of junk pulling right too. Interestingly, watch this really quick. If I say, what's the sum of the forces in X? Well, I've got -2 going left. And then I've got 3.5 and 3.5 going right, which is 7. By the way, why do they even put that weird little circle in there? It's just because how do you put a force on a pipe if there's not something to push on? So it's like they put this weird little random washer in there just so you had something to pull on. Does that make sense? There's really no significance that that thing is there. And that's why they split the 7 into 2 different ones, because if you put it on the top, then you'd think, oh, that's not going to work. It's going to want to rotate, right? And so you see what they're doing there? That didn't make sense to me either for a while. And then I got 2 1.75s, or a total of 3.5 going left. And then I've got 1.5 going left. Oops, I screwed one of those up. No, I didn't. That's good. What does that all equal? Oops, just wrote it in there. Red's my favorite color. What's my favorite color? It's very important that be 0. Do you understand that? It's not because we take statics and we're interested in 0, but if those weren't 0, then the thing slides down the street and it's not going to get longer. Do you see what I'm saying? So if something is sitting there statically, meaning you're pushing on it in different directions, but they all balance, then that will actually cause it to get longer or shorter. But if that is not 0, that won't happen. Now, there won't be any trick questions in the assignment or the test, but just again, I'm trying to learn how to think myself in this stuff and make sense of it, and you should too. But if I'm over there at AB, if I'm, if you will, standing here, Do I know that's happening? The question is yes or no. I mean, that's not necessarily super obvious. Do I know about that?
So
Yeah, and so really the idea is this. In this particular area right here from A to B, I have this force, and I'm going to switch it to pounds, pulling over there. But remember the section concept? Does it make sense if I cut this right here, that the connection between those two pieces that I just kind of thought experimented cut in half, that means that little chunk must also be pulling at 2000, right? Otherwise it is moving. And if I move to here, there's also 2000. Does that make sense? Every place I go. Now, as soon as I hit 3.5, then all of a sudden that's involved. But right now, that whole section AB, that's all you got. So the section concept here is really important in order to make sense of this. And I say that because I suffered a long time to make sense of that myself. Had a hard time kind of getting this in my mind's eye. So do you agree that's what's happening from A to B if that's the only place you're looking right now? And remember, what is that? Well, that's aluminum. So every place in there, the aluminum thinks that's what's happening. You understand that? That's all it knows. So armed with that, this is like problems we did in the last section now. So it's not different, except for I'm just going to use this cool formula that we have now because notice the information that I'm given. I'm given all of this NLAE kind of information. That's what I would be given. And so this formula is a little more user-friendly, I guess you might say. So I'm going to call this sigma, but I'll say AB there just because that's kind of cool. So I have a force of 2000. I'm going to throw the units in here. Let's see if the units work out right. 2000 pounds. How long is that dude? 18 inches. Again, should I be changing it to feet? I don't know. But I got pound inches so far on the top. And then I've got area. Notice up here, they did something very nice for us. They just told us the area. They didn't tell us the diameter and make us calculate it. They just told us what the area is. So it's already an area, 0.09 square inches. And then E, and they also told us that. Notice they didn't make us look it up in the back of the book as we will in all the other problems. And so they said, oh yeah, for aluminum, notice the unit for this because it's kind of confusing. That's 10 times 10 to the third KSI. So the KSI is 1,000 and the 10 to the third is another 1,000. I mean, isn't that weird? So it's really 10 times 10 to the sixth PSI, I guess you could say. I just find that terribly annoying personally. Now, what am I going to write? I'm going to write 10,000 pounds per square inch, PSI, because I just want to look and see like what happens to all these units. Well, first of all, I'm happy to see bunches of pounds and inches. Does that make sense? I'm happy to see a lot of pounds and inches. So just for the fun of it, let's see, the top would be pounds and inches. The bottom we're dividing by square inches, but notice that other one is a fraction. If you divide by a fraction, aren't you multiplying by the reciprocal? You agree with that? So what does all that work out to be? Pounds cancel, inches squared. Oh, inches. Oh yeah, that makes sense. We're talking about that's what delta is. It's a distance, it's a length. Oh, okay, cool, works out. But if they screw with you in the unit, in the units of the problem at all, like it's kind of important to make sure you kind of think about all that stuff. You certainly, when you're done, need to know if the answer is in feet or inches, right? So the point is, okay, cool, all that takes care of itself. So anyway, divide that all junk all out, and I get 0.04 inches.
So if you converted 18 inches into 4 inches, you convert it to feet.
That's right. Then it would have turned into feet. That's exactly right, because all the other inches still would have canceled out, and then we would have had an answer in feet. And in this case, it usually makes sense to choose the smallest unit you could possibly choose because you're going to get tiny distances for this stuff. They're not huge. This is even tiny in inch land. Imagine how small it would be if I divided by 12. Now, do you agree? This is a kind of an important consideration. Do you agree that those arrows are aiming outward? Because remember, it's deforming 0.04 inches, but it is important if it got bigger or smaller. Would you agree with that? It's not just important to say it changed by 0.04. You got to know what direction. So the fact that I drew those arrows out means it got bigger. So notice mine came out positive, which is good because I'm thinking positive is bigger, but it's like, it's something I got to think about.
Put a negative in front of the L when we do the next calculation.
Yeah, so let's think about what happens in the next calculation. So if I get from B to C, and again, don't misunderstand what I'm drawing here. Does it make sense? This is C and this is B. So again, imagine yourself as one of the particles that's making this thing up. Like, what are you experiencing there? You are being pulled to the left 2,000, but then you're being pushed to the right 7,000. Do you agree with that? That's all you know? You don't know there's a 2,000 and a 7,000. What do you feel if you're that chunk of the bar? What's the result of those left and right forces? 7 to the right, 2 to the left. That leaves 5 to the right. Do you agree with that? Now, because this pencil, if you will, is not sliding down the road, what automatically must also be there? What's all of the chunks of it doing? It must be over here pushing back. Does that make sense? One of Newton's laws, and this isn't obvious. I want to give you a chance to think about this a little bit. But you know, when you did do all of that pushing, did the bar move to the right? No, because back up here, didn't we say, no, there was stuff on the right of that pushing back, wasn't there? So if you go to the other side of that, add that up. What do you notice is over here? You got 1.75, 1.75, and 1.5. Hey, look, 5,000. You see what I mean? Like there is 5,000 over there. So it's not that I just stuck it over there.
Wait, so we have the 2,000 pushing along with the 3.5 or the 3,500, and it's pushing against the 1.75.
Yeah, so basically on this side, right here at A, I've got 2,000 pulling to the left, and I've got a total of 7,000 pushing to the right. So right, left, oh, I got to subtract those. 7 to the right, 2 to the left, that'd be 5 to the right. If I come over here, 1.5 plus 1.75, hey, look, 5 over there. So as far as this brown section is concerned, it feels 5,000 pushing this way, it feels 5,000 pushing that way. It's not just that the overall force of this was 0, it's that every section has to be 0. That was the idea of sections in the previous concept, because internally, the bar has to be capable of doing that. So notice that section is experiencing a totally different situation. So what's going to happen to the length of that one then? It's going to get smaller. Isn't that weird? Like the left one actually got larger and the right one actually got smaller. So I got to know that. I can't just calculate this. I got to know, if I call bigger positive, then this one's going to have to be negative. And so was it Ian or Thomas that said, like, you know, we got to get a negative in there somewhere. Was it length or whatever? Well, so this part of it isn't any different. I'm just going to plug and chug. So what's going on from B to C? Well, I got 5,000 pounds. And that distance is not the same. It's only 12 inches, much shorter. And I'm going to leave the units off this time because I can see they're all working. In that section, they told me the cross-sectional area was 0.12 square inches. And they told me that, and I'm going to write this a little more lazy. They said, oh, copper, this is much, well, more. Actually, what does that mean? It's bigger. What does it mean that it's bigger? Does that mean it's going to bend, it's going to get stretch more or less? If the E value is bigger, it's going to stretch less. Two reasons for that. Generally speaking, a big number, you know, a big number makes something larger, but remember E is on the bottom. So if that's bottom, if it's on the bottom, it's actually going to make our delta smaller. So notice it's 18 times 10 to the third, but then KSI is 10 to the third. So that's actually 10 to the sixth. I'm just going to say 18 times 10 to the sixth this time. And so this needs a negative. The question is, where do you put it? And the answer is, who cares? Just recognize that it's compression and put it in there somewhere. You could put it in front of the 5,000 and say that 5,000 is pushing it shorter. I don't think it belongs anywhere else. Like, area is not negative. 12 inches is not negative. The modulus of elasticity is not negative. Put the negative in front of the 5,000 maybe, or just put it in front of the whole thing. But that's why I kind of think it's important to draw this little miniature free body diagram, at least it was for me, to try to make sure I'm understanding this. Because in the end, how long this overall pipe gets larger or smaller, I'm going to end up adding the first one and subtracting the second one. It's possible it doesn't even change size as a result of this, but I'm going to have to add all three of these sigmas together. I'm sorry, these deltas before we're done. So that comes out to be negative 0.0278. And again, it's inches. Okay, so let's move to our final section. Then what's going on with that last one? I'm in that last one now. So I'm just going to make a note that's from C to D. What's it experiencing? Again, look to both sides of it. What's it got? Well, it's got 1.5 pushing on the left of it, which is 1500. Automatically, I don't even have to do the calculation. I know the right's also 1500 because it's not moving. They have to balance or there would be no stretching involved here. But add all the other ones up. A second ago, we saw that there was 5,000 pushing that to the right. No left. No right. Yeah, I won't take the time to do that. So 1500 there as well. Notice this is also negative. It's actually getting smaller. It's under compression as well. So this one's actually getting smaller. So then what is delta, the change of CD? Its force is negative 1500, at least that's where I'm going to put that compression in. Its length, how long is it? Oh, it's 16 inches long. And its cross-sectional area, again, I have to calculate it. They told me, ooh, tiny, 0.006. And its E value is 29 times 10 to the 6th. So that delta value, because I punched this in already, is negative 0.0138. So, thank you. Is that true? Sure is. Thank you. Good catch. And so if I want to know the overall change, then I just need to add all of those up. And again, you can see why it's important to understand some are positive, some are negative. But did you notice, although, you know, my first thought was, oh, it's going to be negative because look, there's more negatives than positives. But notice that first one was a fairly flexible material and it actually got 0.04 bigger. And the other two, although they got smaller, weren't together as big. And so this actually just got a hair bigger. Actually, that may not be true.
Yeah, that's slightly smaller.
Yeah, it's slightly negative. I didn't write a negative, but I had the word shorter inside there, so didn't notice that till just now. So this is kind of a good problem because it's like it was almost zero. Does that make sense? It almost didn't change at all. But did the individual members of it change? Yeah, they actually changed a bunch. So in one sense, this actually isn't really new. Now, good news. What else do I have to teach you? Nothing. That's it. Like this concept, we just need to kind of play with it a little bit and see if we can get better at it. So this is neat because it allows us to have multiple materials now and different forces and kind of figure out each one separately. And it seems like we're going to be awesome. Let's see. Let's do the last one. Good question. Gosh, I thought the same thing. Is it like somebody invented it during that time period?
Some of the numbers are high the carbon, at least for steel. And 20% of carbon in one, and the other one is the type of steel or something like that.
Mhm. Yeah, I know the alloys, because an alloy means they mixed a bunch of different kinds together. Because some steels are brittle and really stiff and don't want to bend much, but then they break a little easier, and so.
See it on pocket knives and stuff.
Mhm. So I want you to stare at this one for just a second. It's probably not, I'll turn sideways. You got it in front of you, so you're probably not even looking at mine, but how is this different, or is it even different?
Is this one? No.
So let's just scope that really quick. If I said, okay, what's the sum of the forces in X? I've got 8 moving left. I've got 4 moving right. I've got 6 moving right. I got 2 moving left. What's that add up to? -4. It adds up to nothing. So it isn't moving. It's not sliding along. Again, as I said, they're not going to make a trick question. It's always for you here. So that those forces will always be 0, because if they're not, then this thing is not going to change size. So they haven't fooled with that. That's
So,
great.
Your last section only has like one force.
Yeah. Isn't that interesting?
So I don't know how I draw that free body diagram. Actually, it's just not moving, right? We don't have to do that one. It's not being pulled or pushed.
Just ignore it.
That's
Yeah.
exactly right. In other words, if this last little coupling right here started moving left, everything here would just go with it. Like it's not going to stretch. Now, if they told us that was like glued to the wall or welded to the wall or something, then that'd be different. And incidentally, that's kind of where we're going next with this. If you have a couple of things, if you have it pinned in there in such a way that it wants to expand, but then it's like stuck against 2 walls, does it make sense? That's going to create a normal stress inside the member, and it's going to have to be able to withstand that, or it'll break like that piece of concrete. So yeah, that's exactly right. There's basically nothing happening to DE. There's nothing over there. What's different about this? The answer is almost nothing, except for this time they just told us what kind of material it is. So that means I have to go look up the E value myself. So it's actually a better question. And they told us the diameter of it. So that means I have to figure the area myself, but it's the same exact question.
Once you get those two things, it's not different materials, right? It's just kind of just plug the different lengths in.
Exactly. Yeah, and this is interesting because that's the same exact material all the way through and the same size all the way through. I think it's a little more interesting when they're all different sizes, kind of like the last one. That's why I did that. So-
Well, is BC and CD, I guess just intuitively. No, I guess it won't. I was wondering if they would just be the same, right? But one you'd have a force of 4, and the other one you'd have a force of 2. So it'd be slightly different.
Yeah, I mean, I still think the section thing kind of bothered me here for a while. I had a hard time figuring this out until I just said, okay, just look at A, B only. So here it is. And I'm thinking of it as a section like this. And I know over there on the right, I've got this thing being pulled at 8,000 newtons to the left. And so no matter where that chop is, that must be counteracting that by pulling 8,000 newtons to the right. And that's all there is between A and B. Now, as soon as you get past B, then suddenly 4 gets applied, right? Isn't that 4 right there? That gets applied, but it's like from A to B, that's not there yet. Again, I don't think this is obvious. This is kind of hard. So that's A, that's B. That's kind of my free body diagram. Doesn't matter where I put that cut, as long as it's 0 to 4. So notice the area of this would be pi times radius squared. It's, and again, I'm kind of wondering, you know, can I leave that in millimeters? Should I turn it into meters? I don't know. Let's let the unit speak this time and we'll kind of see. This is probably good to at least look at because it's metric this time. So you got your chart in front of you. I'm going to pull that up and I'm in metric land. So what is the E value for, it was this one, right? This 2014 T6, like there's its modulus of elasticity, 10 to the sixth. I'm sorry, 10.6 times 10 to the sixth PSI.
We're in metric.
Metric. I just got done telling you how important it was to look at the right table and then I didn't do it. 73.1. Again, probably -0 on a test, but everybody still died, right? So 73.1 gigapascal. What's the unit for that? Because remember, pascals are like not going to help us here for units all to cancel. What the heck was a pascal? Newtons per square meter. So think if you need to get it back, think of PSI. PSI is pounds per square inch. Oh, force divided by an area. How is force measured? Newtons. How's area measured? Meters. Oh, newtons per square meter. Like you can get it back.
So can we think of this as if we want to like mimic the top is 73.1 times 10 to the third kilonewtons?
Yes,
Cool.
that's exactly right. Or just switch it all to newtons. That's so yeah, some version of that. Again, I'm always kind of losing it, so I feel like I have to kind of hang on to this. So I'm going to write 73.1 times 10 to the, it was mega, no, it was giga, right? 9. And that's newtons per square meter. So that's what I'm going to switch everything in newtons and meters because I'm going to screw it up if I don't. Like that's my logic. Okay, so cool. So what's sigma here? Sigma of AB, we said it was N the force, 8,000 newtons. Sticking the units in there, times the distance. The distance is 4 meters. Okay, good. I'm happy with meters. Everything is just like last time, everything was pounds and inches. This time, everything's going to be newtons and meters. And then it was area, which I won't calculate the number for, but notice, in a sense, I'm finding myself thinking, yeah, I'm glad that I called that meters because I want everything to be newtons and meters. And then this E value, which is 73.1 times 10 to the 9th times newtons per square meter. But again, let's look at the units of this. So that would be newtons times meters on top, and then square meters because of the area, right? And then I'm dividing by newtons per square meter on the bottom. So that would be times meters squared on the top and newtons on the bottom. Is that okay? What's that? No, because I cut this in half myself this time. I took the diameter and I said, oh, half of that I can do in my head. That's 15. So I decided to do it with pi r squared rather than pi over 4 d squared. They're both fine. It's just less to write down, less fractions. So let's see what happens to all that stuff. Let's switch to red. Newtons are gone. Square meters are, oh, look, it ended up in meters. That's good because we needed a length, right? Now, is that a good place to end up? Do you want to measure something getting longer in meters? No, probably millimeters. Interestingly, if we had left this one, not left it, but if we changed that to millimeters and called that 4,000 millimeters, that's probably actually better.
Your area would have to stay in millimeters as well.
Well, notice this square meters canceled with this square meters. So those had to stay meters, but this top one up here is kind of all by itself. It's just kind of interesting to think about. Like this is the power of what units are.
So Doug, what did you get? Sorry.
So anyway, if I punch all that in, I should get 0.0006193.
I got 6193 times 10 negative 10, but I stayed in. I went to Killa.
Yeah, and that's why I don't do it, because I get all concerned, like, oh crap, am I gonna, do I move, like, do I get at it? Because you don't want kilometers or something, you know, like kilometers, you don't want the answer to be measured in
Oh, is
kilometers.
that what it's measuring, right?
So it's like, it's probably that, and so that's exactly why I like, I don't trust myself. Maybe after I found myself really hard, like watching the way the author did things, because he's good at it, you know, like I'm not good at it, I'm just figuring this out, so he would do everything super quick, just like you were doing, but it's like, I couldn't hang.
I just had a lot
First
of
time
luck
through.
because everything's
Yeah.
given to us in kilo land.
Absolutely.
And so up until now, I've had no issues, but now I got your exact same answer, but now I'm off by like 7 zeros, like a lot of zeros.
Yeah.
And I'm wondering,
Well, and as I said, like, even if your answer, because remember, when you say kilometers, you're 3 more zeros beyond it, because I'm in meters and you're thousands of them. So your decimal place should be 3 more places to the left from mine, because I'm in meters,
you know,
you're
where I
in
might have went wrong
kilometers.
is my area equation, because I kept those in meters.
So I do think it's important to kind of, this is the one place, I'm always pretty lazy about units in this class, but I'm conscious of them. And here it's like, I'm going to have to actually write them down. I'm probably going to get this problem wrong. But to your point, if you're doing this and you answer kilometers for your answer, or 10 to the 3rd meters, it's like, that's fine. I mean, is it weird? Would anybody do that in the real world? Probably not, but it's like, in the end, you have to kind of convert something. I just find it easier to do it from the start, even though I have these gigantic numbers, which is obviously the advantage of what you're saying. But the cool thing is if you type all the gigantic numbers in your calculator just once and for all, then the answer pops out and it's already kind of correct. Of course, if you want to convert, you'd have to say, well, in 1 meter, there's 1,000 millimeters. Oh, I multiply by 1,000. So the, you know, the answer in the back of the book for this is almost certainly going to be 0.62619 or whatever millimeters. Like, that's a much better answer. Do you agree with that? It's like 0.5 millimeter. Yeah, well, no kidding. It didn't get very much longer. 0.5 millimeter. Can't even see that.
You know, all of my area. There we go. All right.
So anyway, I think just to make sure we have time for the last one, I want to switch to that one. But yeah, just out of interest, I'm going to go over there to DE. I'm not going to do this whole thing, but in DE, stare at DE for just a second. What's going on at DE? Well, I've got 8 to the left. I've got 4 to the right. Okay, so that's 4 to the left. But then I got 6 to the right. So now that's 2 to the right. Well, then I got 2 to the left. There's actually no force there at all. There is 0 force going that direction if I add up all the forces to the left, which means this has no force on it, which means its sigma value is nothing. It's not going to change length. That right side is just going to slide along for the right, nothing connected to it. So not obvious to me, but that's definitely true. You know, you have homework assignments, but if you're just, I guess you have this in the back of the book, but if you're just curious, it's 0.6967. And that's everything included from A all the way to E.
That's a growth, right? Oh, you're in millimeters.
Yeah, I think I'm in millimeters. Yeah, everything I have on my notes is millimeters. Okay, so let's look at one more question. That's just kind of neater, because it's a little more of a complicated sort of a shape, a little bit more of a typical shape. 3-pin connected A992 steel, so it's all the same steel. They're telling us it's got 1.25 inch diameter. Again, that's a pretty big size. determine, and this is backwards though, determine the magnitude of the force P needed to displace B 0.25 inches to the right. So this is supposed to go bam and be like a quarter of an inch move to the right. So this is weirder because before we were given the forces and then asked for how much it moved, and this is saying, no, I know how much I want it to move. Well, then how hard do you have to pull to get it to move that far? Quarter inch is pretty far. Do you agree with that? That's actually pretty, I mean, if you're talking steel, that's a pretty big pull. Notice the connections here are like pin connections that would allow this to actually be flexible. Can you appreciate that this is going to end up kind of going like that? It's not just going to stay, the angle is going to get all screwed up here. It's not going to stay whatever it is, whatever it was before. So this is actually kind of hard. Let's stare at this a little bit.
We're gonna have to maybe add up all the feet of steel together, and then you're gonna have to increase each.
Well, interestingly, because the length of each one of those is different, I kind of have to do them separately. Notice this is rather nice, but because this is 3 feet horizontally and 4 feet vertically, then that means this is 5 feet long exactly. So Pythagorean theorem, that's 5 feet long. So one is 5 feet, one is 6 feet. So there is more than one way to do this.
So this has kind of been new past, but cumulatively, if you do them one at a time, you can still use 0.25, right? And that'll equal cumulative growth of 0.25.
Yeah.
Overall.
So the only difference this time is like this 6 foot part here is like, okay, we did that a second ago. I get I'm pulling, but now all of a sudden, what about that angled one? That's like pulling in a totally different direction. But remember, the force has to be pulling axially on it. That P is not pulling in the right direction. If you pulled on that CA linkage with an angle sideways like that, it's gonna switch directions and get longer. Does it make sense? That's like not good. What I really need is to kind of pull on this thing in that direction. So I need to actually convert that. So let's talk about that. First of all, just to look it up, A992 steel, if you look it up in the back, is 29 times 10 to the 6th PSI, because I'm looking at the top chart this time. So I'm going to write it like that because I'm worried about units. So it's like I need the E value. Great, I looked that up. Awesome. But let's draw a kind of a quick free body diagram here. So if I pull to the right, and this is A, if I pull to the right with P, and this is pulling off in this direction, that's pulling off in that direction. Do you notice that's symmetrical? Which means I don't have to give these two different names. I could give them the same name this time. And so again, for any of the stretching to happen, does it make sense the sum of the forces at that spot has to be 0? Can you tell that the sum of the forces in Y is automatically going to be 0 here without having to do the calculation? P doesn't do anything to it, but the other two are pulling exactly up and down at exactly the same size because they're both 3, 4, 5. So I don't really need that. What I really need is the sum of the forces in X to be 0. Well, what do I have? I've got P pulling to the right, and then I've got F pulling to the left. But what's the modification? Because it's not pulling left, it's pulling at a weird angle. What proportion of it is pulling left? 3/5 of it. And then don't I have another one of those? 2 of them. So I could write minus F 3/5 again, or I could just say times 2 here.
Well, 2 at 3/5 equals P.
That's exactly right. So you can say that P equals 6/5 F. Does that make sense now? That's the connection. Or, I don't know if we need this, but couldn't I solve for F by saying F is 5/6 P? So now I don't need F anymore. Like this is the one I want actually, now that I think about it. Because now I don't have 2 letters. I have P and I have 5/6 of P. Whatever P is, that's 5/6 of it.
So you draw your free body down. I thought it was just going to be P both ways, but now it's P to the right and then 5/6 P to the left.
That's exactly right. But it is both places. Don't forget. It's like 5/6 P there and 5/6 P over here. But those 2 bars are going to behave the same.
So this is 5/6 P in the X direction. So when we draw a free
No, it's actually not, because the 3/5 part took care of that. So this is literally that angled line. If I'd have just called it F, as though F was horizontal like this, then I would have to make that conversion, but I called it 3/5 of F. Therefore, it literally is. I'll go ahead and write it in there. This literally is 5/6 of P, and this is as well.
Wait, Doug, why did you take 3/5?
Because this thing is pulling, so it's pulling that far 3, and then its hypotenuse is 5. So basically 3/5 of it is what is vertical. 3 out of 5 parts of it, I'm sorry, are horizontal. 3 out of 5 parts of that are horizontal. Okay, I'm actually ready to rock with what we just did. I can say, okay, cool. What's happening from, actually, let's do the easy one first, from A to B. As before, I'm doing the easy one first. As before, if this thing is pulling P to the right, then it's also pulling P to the left. Again, I'm thinking of that as a section. It's like somewhere I chopped it right there. So if it's actually stuck, the sum of the forces are indeed 0. We just kind of made sure that was going to happen. Then this thing will be changing size. So I'll rewrite the formula up here. Sigma is N times L over A times E. So my normal force is P. My length is 6 feet. Let's see, feet. I'm thinking this probably should be inches. Divided by the area. This time I've got 1 1/4 for a diameter. I can't really cut that in half in my head very well, so I don't trust myself. I'm going to use the diameter version. And then I've got my E value of 29 times 10 to the 6th PSI, pounds per square inch. Oh, look, everything is pounds, everything is inches. I'm good. I'm gonna get my answer in inches then. Awesome. But notice I don't get an answer because I don't know what P is. Like I just have an equation here. And I don't like my equation because it's got 2 unknowns in it. It's got that and that. So it's like, that's not good.
Well, you know, maybe it's 2.4.
Yes, except for part of that stretch is coming from AB, but the other part of it's coming from AC. So I can't set that equal to 0.25.
So that's what I was thinking, like, if we make AB 0.25 inches longer, yeah, it would work. It would have to be a ratio.
That's right.
Well, couldn't you make it a ratio? So if you
Well,
did
you
the,
had for,
Yep.
strain, because you do have the change in length on that. It's gonna want it to go 0.25 inches.
right, but
And
we
then
need
the
to
original
do
length.
0.25 of 6 feet and then make that, because that makes it a ratio, and then you can ratio it.
Which is your strain. And then you can use your strain to find your and you have your modulus of elasticity, so you can find your sigma, which is your normal strain, stress, and then you can find for P.
Once you find the everything else you support in.
So you're exactly right. Like we got to come up with some kind of ratio here, but the safest thing to do, if I'm not sure, is to say, well, I'm just going to consider this axially. The only time anything stretches is axially. So I have 5/6 P pulling on both sides of that. Do you agree with that? And so I'm not thinking of this as horizontal. I'm just literally wondering how much longer AC gets. Not horizontally, just literally hypotenuse. It was 60 inches. How much longer is it going to get? And that's what I'm trying to calculate here. So its force is 5/6 of whatever P is. Its length is 5 feet, which is 60 inches. The area has not changed. And neither has the material strength. So again, I'm not very happy with that number.
If you can do the shear. Do we know new?
So I'm not very happy with these two, but do you agree that, I can't say delta AB plus delta AC is equal to 0.25? Because AC is pulling at an angle, right? So it's like, I gotta somehow figure that out. Well, I'm gonna do it kind of old school. So does this make sense? If I switch this to, does it make sense? I have P over there and then just times a bazillion numbers. So I'm just gonna multiply all those bazillion numbers out. Turns out you get 0.0345, 1405. Now, what does that number mean? Remember, that's inches. Like, that's how many inches bigger it gets.
That means it grew that much times P.
So do you agree this side then is 60 point, all of those decimals I just put there? It used to be 60, but didn't it just get bigger by 0.000, right? For me personally, actually, I can't say that because that had a P in it, didn't it? I can say this. It's 60 plus that. I can't just add it because it wasn't just a number, right? So that's how much bigger it got. Well, that's not really very helpful. Don't I actually need to know how long this is? So, everybody okay? Because it's 5 feet. It used to be 5 feet, 60 inches, and then it grew. So don't I know this and this now? Like, what do you have to do with those two numbers in order to get the one that I actually want to know? That's exactly right. So if I said, I don't know if this is a good way to say this, but if I said sigma AC and I said like horizontal, does it make sense? It would be the square root of the hypotenuse. There's the hypotenuse squared minus 4 squared, except for I'm doing this in inches, so I'm thinking of that as 48 squared. Again, I don't know if this is the best way to do this. I'm just trying to draw pictures and like make sense of it in a way that I understand. There's probably some ratio shortcut, something kind of cool in here, but it's like I can't do shortcuts until later. Like I got to do this a lot. And I like to like see it, I like to touch it, and I want to make sense of it. So that's actually how much longer it just got. Do you agree with that? That's actually the answer. Oh, okay, well then I'm home free. I'm done, kind of done. Let's go back up here. And I want to do the same thing just to make it look a little nicer. Like up here. Up here, what is sigma AB? Well, again, isn't it P times a bunch of numbers all multiplied out? So if you multiply that out, you get 5 zeros, 2023. So that's how much longer that got. This is how much longer this got. And now if I add those two expressions to each other, that's equal to 0.25. You cool with that? And can you see why scientific notation gets invented? Like that might be nice to call that 2 times 10 to the -7th or whatever, something of that nature. Fine. can't be done without an iPad anymore. It's impossible.
We have to do linear algebra without a tablet. Government does. Make freaking matrices.
And that added together would be equal to 0.25. Now, do I like that equation?
Yeah.
I like it because it's got P in it. I don't like it because it looks awful. So if I'm an engineer, I'm putting this in Desmos. But you have to be good at algebra. You can't square both sides right now. And the fact that there's a plus sign means you're gonna have to do the distributive law with the little smiling George thing. You know, it's like first one times the second one times the first one. Like if you squared both sides, you'd end up with a quadratic equation for this, and then you have to put in the quadratic formula. And so it's very possible to do this by hand. In one sense, I want to say, you know, as a math lover, you should be able to do it, but let's not say we did, right? So I'm gonna write here Desmos and say P equals 57,314.7 pounds. Of course, that's going to be in the back of the book as 57.3 kips, right? But that's not a super important question to me. But the concept that you can have something at a couple of angles and pull on it and have to kind of deal with the complexity of that is a thing. But generally speaking, most materials, they're axial. If you think about all like the members on a bridge, you know, they're all at a bunch of angles and stuff, but each one is considered axially. And then if you just have to convert it like we did to be horizontal to see how much the overall bridge grows or whatever, it's like, okay, I can do that. But the main thing I want you to see here, besides, you know, maybe getting a little bit better at geometry, is the monumental pain in the butt it is if you don't know the force and then you're asked for the delta. But in our case, we were kind of told delta, hey, this thing's going to get longer, go find the force. Ooh, I just like, I couldn't take this calculation up here and turn it into, I couldn't take that calculation and get an answer. Like I just had this big disaster. But on a second note, you agree that writing it like that, although rounding crazy and so forth, and that doesn't look so bad now. Like I can at least live with it. What do you think?
I think I want to check my way. I want to see that.
Yeah, I love that. Extra credit, certainly if you spend any time trying to kind of like figure out a less blue collar way of approaching this. Is there some kind of shortcut or something that would be a little bit better? I don't know the answer to this, but my gut feeling is 3/5 was horizontal, right? That was the horizontal conversion. So couldn't I just take it times 3/5? Like instead of the Pythagorean theorem, couldn't I just take that angled force and just say times 3/5, and now it's horizontal
Right.
instead of doing Pythagorean theorem?
So my question. So
But I'm just not sure. So
yeah, go back up and you got delta AB or whatever. With those two equations, I feel like you had everything because we need to grow this entire thing by 0.25 inches. So can't we just take the ratio? So if that's 6 feet long, that's 72 inches.
It's only taking B as it itself only stretching. not
Yeah,
the
but if you
other
take at 0.25, if you take, so hang on, so it's 72 inches divided by, is that how I did it? 0.25 inches? What did I do that?
Yeah, you're talking about the strain, right?
No, that's not right. Other way.
are you, because I heard some of you saying this earlier, kind of thinking about, is there some way we could use some of the other equations we have, like strain
Yeah, it was only
equations?
acting on that number. We weren't taking account of the two other members coming in to also increase that length. We're assuming that only AB was growing.
Correct. Yeah, which you definitely can't assume. My question is this, just take a look at this because I'm going to erase it, but basically if I take that sigma or that delta AB right there, which was okay because it was horizontal, right? It was already horizontal. And then I add it to sigma AC, delta, keep saying it wrong, delta AC, which was this one over here, but then I say, oh, that was the weird one. I just have to modify it to horizontal, 3/5. And then set that equal to 0.25. Would that work? Wouldn't surprise me if it did. And that equals 0.25, and it's like, hey, it saved me a bunch of time.
Yeah, you guys still are. You can plug in this tool and then just apply P and define that one, 125 by 4 little school jumps added together, but we still have to. And if you, because you put the A, B, and H in there.
I mean, it's a length.
Remove
I'm actually ready to say I'm almost sure this will work because it's a length, isn't it?
the top and the bottom added together without P.
Delta AC is a length. So
We're saying we'll just put delta AC.
didn't we do that with other lengths?
Because the X portion. The X portion. And it will, we think, we have.
The other thing that worries me though is these decimals are so stinking tiny that rounding could really cause a huge problem here. The fact that 1405, I don't remember what that used to be, but it's possible it
Times its X portion.
might not be obvious.
Well, yeah. But we don't know.
Oh, so we modify it.
So what was our answer again?
But we
We still have
want
to do all that.
We have, well, yes,
Answer.
but not.
So I would do
this portion with
0.25 divided by 3/5, and then you can add the P's. Right? Or is that
the-
wrong?
Oh,
No, you can't divide by 3/5 because distributive law on the other side, they both have to get divided by 3/5.
Right.
So no, you got to add them together. You got P times ugly number plus 3/5 times ugly number times P. So you got to add those two together.
Okay. So if I want
What I would have done is remove the.
Yeah, well, I mean, it's within
Numbers in it together.
the
And then divide
same,
the whole thing.
I
mean, divide 2.5.
how would you say it, like range, like I got 87,000, this is 57,000. So I'm wondering the decimals
Yeah,
are.
that's exactly, those decimals going to make a huge difference. They're really tiny and you're going to be dividing by them. And when you divide by a really tiny decimal, it makes a huge, huge difference.
So we just need to be keeping all of our values in there.
I just don't like that. All right, get on Desmos, like you can't do it in your head. You can't
Yeah.
do it.
Well,
Yeah.
I like, here's a trick.
Yeah, I bet you do.
But here's a trick for doing area. Hide with it. Don't multiply by it. You carry it with you as you go. It gives you a more solid answer.